is really all about dot product and orthogonality or perpendicularity and of an optimization problem. We're actually going to, if you've ever done linear regression or least squares regression, we're actually going to derive that process of fitting a line to data points using linear algebra, of all things. So it's sort of cool. But just before we do that, I kept saying I was going to give you a reason why somebody might care about matrices being similar to each other. So say A is n by n, and A is similar to a diagonal matrix D. So A is equal to P D P inverse, where D is a diagonal matrix. And so here's where this similarity type of thing comes in handy. And calculations. Say we need a to the 50th power. And that it's not unusual to need powers of matrices in computation. So imagine this is like a 50 by 50 matrix, and you're asking a computer to compute the 50th power of it. That's a really complex calculation. And when you get into these messy calculations, round off becomes a huge problem too when you're doing lots of multiplications and additions. So it's actually easier to compute P D P inverse to the 50th power, like way easier. And that doesn't seem very obvious to me, because we're replacing one matrix with three. Okay, D is simpler, but P and P inverse could be really complicated. To the 50th power, like, it doesn't seem to have made life better, right? You should think, what does that do? But if you think of writing that out, P D P inverse times P D P inverse times P D P inverse, on and on and on, till you get to 50 of them, there's this great simplification that happens. Because you keep, in the middle of this multiplication, you have P inverse times P over and over again down the line. And so those are all going to cancel out. And you're going to end up with P and a whole bunch of D's. You're going to have D to the 50th power P inverse. So you actually, in this special situation, you end up with just one copy of P and one copy of P inverse. Now, computing D to the 50th power, a diagonal matrix to the 50th power, is easy. Like if you take 2, 3, 4, and raise that to the 50th power, that's just going to be 2 to the 50th, 3 to the 50th, 4 to the 50th power. So it's really just raising constants to a power. There aren't all these other calculations involved. So this is easy. Multiplying by P inverse could be really complicated. P could be complicated. But it's like you have two complicated matrix multiplications instead of 50 complicated matrix multiplications. So that's where the great simplification. Now, not all square matrices are similar to diagonal matrices. Many are not. So linear algebra gets a lot more complicated when you work with matrices that are not similar to diagonals. And what people have done, it turns out every square matrix is similar to a matrix that's almost diagonal. There's something called Jordan form that's almost diagonal. And if we had more time or a heavier course, we'd go into that. And so there are other kinds of relationships that are used in calculations for matrices that are not similar to diagonal. So sometimes this is called a factorization, because it's like we're writing A as a product of other matrices. There are other kinds of factorizations out there in linear algebra that are very useful for calculation, but we're not going to talk about it. Okay, that's all I want to say about that, unless you got a comment or a thought. But to me, that's a nice concrete example, pretty much, of why similarity can be useful for calculation. Now we're going to plunge into 6.1. Does anybody need a 6.1? You should. Most of you have them, I think. And a lot of this is going to be familiar in 6.1 from your 110C experience. So let's see. But then there's going to be, by the time we get to the there's going to be something totally new and different from 110C kind of stuff. Chapter 6. When you take that definition of vector space from chapter 4, if you need a 6.1, let me know. You may have it already. There's no concept of length, of distance, or of angle. Now, we have a concept of length, distance, and angle, because in 110C, we learned more, we learned that way of thinking of vectors in R3 and R2. But just from the general definition of vector space, there's no concept of length, distance, or angle. We can add these concepts if we define something called an inner product. Okay? Do we need 6.1? Anybody realizing they need 6.1? Okay. Up. Am I? Oh. It goes down to just looking like the battery that's on, or should it be more? It's good? You think we're good? Think we're getting sound? Okay. Okay. So we're going to define inner product for Rn. It's pretty much the same thing as dot product that you learn at 110C. All right? But just be aware, we're going to talk about inner product for some of these other vector spaces, like vector spaces of functions or polynomials. And then your intuition about dot product isn't going to be quite the same, because we're going to get a little bit more abstract. So just don't about dot product. But you know a lot. So let U and V be two vectors in Rn. So there's U and V with components. The inner product or dot product of U and V is defined by that expression in the box, where we're just multiplying corresponding components and adding things up. So this is based on the standard basis. So we did all this talk about how vectors can be described in different bases. The inner product is just defined from the standard basis form. So, because of course that if you use different coordinates, that would come out different. So you have to we're fixing with standard basis here. And it's just a number when you add all these up. You're just going to get a scalar quantity. Some people like to define the inner product using matrix multiplication. So if U and V are both n by 1 matrices, right? Their column vectors are n by 1 matrices. U transpose is 1 by n. So we could multiply U transpose times V, thinking of those as matrices. So you're multiplying a 1 by n by a n by 1. And what you're going to get is a 1 by 1 matrix, which is the same thing as the dot product. So just, I'm not going to use that transpose notation too much, but you might see it in the book. And there's an example where we go ahead and calculate, and you're like, yeah, put a whole bunch of these on the final, right? Like, just ask us to calculate the dot product, right? All right, so you guys are familiar with that. Properties of inner product, I think the basic stuff here you're familiar with. It's commutative, comes out the same way if you change the order. You can distribute dot product over addition. You can factor a scalar out from a dot product. And an important property of dot product that we're going to use is that the dot product's always positive. It never, inner product never comes out to be a negative number. And it comes out to be 0 if and only if U is the 0 vector. So for any non-zero vector, a dot, I think I said something wrong. Did I say dot product never comes out to be negative? I shouldn't have said that. Dot product can be negative. Dot product of a vector with itself is never negative. So here we're looking at a very particular instance of U dotted itself, okay? When you dot a vector with itself, you always get a positive number, or you can get 0 if it's a 0 vector, okay? But the dot product of two different vectors can definitely come out to be negative. It often does. And these properties are easy to verify. Notice that U dot U is just the sum of the squares of the components. So you see that positivity really easy here. The only way the sum of that squares could come out to be 0 is if each component is actually equal to 0. The length or norm of a vector we can now define is denoted with these double bars. And it's just the square root of the vector dotted with itself. So it's the same expression you're familiar with from 110C, except now we're dealing with R3 or R2. You think about what this means, but we're going to use this idea of length or norm even with the polynomial vector spaces. You could get out a ruler and measure something to see how long it is. Like, how long is a function, right? That's going to be a little bit more abstract. So you can't really measure how long a function is. You just define an inner product, and then you define the norm by this formula. The length of a vector squared is the same as a vector dotted with itself. If you have a scalar times a vector, you can factor out the scalar from the length calculation, but that scalar will come out as absolute value as far as length is concerned, okay? And also just note that the length of the opposite of a vector is always equal to the length of that vector, okay? Little properties where you're probably already worked with. And I think you're also familiar with this terminology. If a vector has length 1, we call it a unit vector. And there's nothing positive about a unit vector, right? It just means its length is 1. So if v is a unit vector, minus v is also a unit vector. You know, if you're familiar with I, j, k, those are some unit vectors. Minus I, minus j, minus k are also unit vectors in 110C terminology. And so here's just an example. U is that vector in R4. And here's the length of U, square root of 10. I know, I just pulled that out of blue. We say two non-zero vectors have the same direction if one is a scalar multiple of the other, and that scalar is positive. So if U is a positive scalar multiple of V, we say they have the same direction. If that scalar multiple is negative, we say the vectors have the opposite direction. And that totally matches up with your intuition of dealing with arrows. So you're like, okay, hey, so far so good with 6.1. Next page. Here, I think you're also familiar with this kind of calculation. Same U as before. The length of U was square root of 10. We're defining a new vector, W, to be 1 over the length of U, which is a scalar, times the vector U. And this is what it looks like. And it looks like a big mess. But W is a unit vector in the same direction as U. And I know when I teach 110C, we spend a lot of time working with unit vectors in the same direction as a given vector. And sometimes you just say you divide the vector by its length or its magnitude or its norm. Those all mean the same thing. So length, magnitude, norm of a vector, those are all equivalent. Three different ways of saying the same thing. There's not a distinction made there. And so any non-zero vector has one unit vector pointing in its same direction, and there's a unit vector pointing in the opposite direction. Makes me think of directional derivative of vectors from 110C. Okay. And just, again, this unit vector business, I know I used to always think, when I was a student, I thought, unit vectors sound simple. How come they always look so complicated when you actually write one down? So just convince yourself that if you compute the length of this guy, excuse me, it's just going to come out to be 1, right? We're setting it up so that when you add up the squares of those components, take square root, you have just 1. We can talk about the distance between two vectors, u and v, and that's defined to be the length of u minus v. Now, if we think of u and v as points in Rn, or R3, if you will, this matches up exactly with the distance formula in R3 or R2, and of course it applies to Rn now. So you can't talk about distance between arrows so much. We would go to the point metaphor, or the reality that these vectors are points. The distance between the 2 points they represent is exactly what this guy gives us. And so there's a simple example there from R2, a general situation from R2, u and v are vectors in R2. This distance between u and v just comes out to be the distance formula in R2 that I'm going to be talking about in my pre-calculus class today, so same thing. Now we also have distance in R3, R4, R5, all the way up to whatever. And another comment about 110C, Calc 3, you learn that there's another way to describe the inner product of two vectors, right? You've seen this formula before where you take the length of u times the length of v times the cosine of the angle between. And we're not really going to make use of that formula, but we are going to make use of the idea that if the angle between is 90 degrees, then cosine theta is 0, right? Cosine of 90 degrees is 0. So this comes out to be 0. And so this product is 0. That means u dot v is 0 when the angle between two vectors is 90 degrees. Turn the page. So we're gonna generalize this idea to Rn now. Now we don't have degrees, we don't have angles. We're only going to have one angle in a sense that we care about. So let u and v be vectors in Rn. We're going to say u and v are orthogonal if their inner product is equal to 0, right? If their dot product is equal to 0. The intuition is that they're perpendicular to each other, okay? So certainly that's going to be true with the arrow representation of vectors in R2 and R3. And there's a similar way of thinking about things in higher levels of Rn. But we're also going to talk about orthogonality eventually in these abstract spaces. Like we'll talk about two functions being orthogonal to each other. And there's no right angle there. It just means that this guy is true, that the inner product of the two vectors is 0. We'll also agree that the 0 vector is orthogonal to every vector. That's just convenience. There's no way, you can't draw a picture of that. There's no sense to it. It allows us to not have to make an exception for 0 each time. Okay, now I realize, just wait, we're going to come back to this. I don't know why I put this statement here. I think that's sort of a mistake. We're going to talk about the Pythagorean theorem for a second, and then we'll come back to that statement up above. Really, I should have put the Pythagorean theorem next. And this is just your familiar Pythagorean theorem, but we're generalizing to Rn. And if u and v are orthogonal vectors, so we have this sense that they're perpendicular to each other, if and only if the length of u plus v squared is equal to the length of u squared plus the length of v squared. So that should kind of look like your a squared plus b squared equals c squared. Pythagorean formula from geometry. Let's see, if we were to draw a picture of, let's say, here's u, here's v. u plus v, now I can get by completing the parallelogram. And now I can think of this as a copy of u, if I use that arrow representation of vectors. So notice the only point I'm trying to make here is geometrically, you can think of copies of the arrow representation of uv and u plus v as sides of a triangle. And u and v are going to be perpendicular to each other, form a 90-degree angle, if and only if this condition is satisfied, which is like saying this length plus this length is equal to that length. U plus v would be like the hypotenuse of the right triangle. So this is not a Pythagorean situation the way I drew this picture, right? You'd have to have a right angle up at that corner. So that's the relationship to Pythagorean theorem. What I want you guys to think about is this proof. So we've had, somewhere along the way, I made this statement that the magnitude of or the length of a vector squared is the same as the inner product of that vector with itself, right? So what we're going to do is we're going to try to prove this working from this idea and not using components of vectors. You could write it out in terms of components of vectors. It's not hard. It's perfectly fine to do it that way. But notice this slightly fancy way of proving this. And instead of w, we're thinking of this u plus v as a single vector, okay? So applying this idea from, I think it's on the previous page, to the length of u plus v squared, that's got to be equal to u plus v dot u plus v, just so that first line makes some sense for you, right? Right here. And then we can apply those distributive property, the distributive property of inner product from one of the earlier pages a couple times, and we get the sum of four dot products. These two are the same, so again, it looks a lot like square of a binomial, even though you can't say vector squared. That doesn't make any sense. You can say the magnitude of a vector squared. That makes sense. You can square a real number, but you can't square a vector. So don't ever write this. If you want to dot a vector with itself, you got to write it out. There's no shorthand for that. It's u dot u, okay? But again, u dot u is equal to the length of u squared plus this thing plus the length of v squared. And we know this term is equal to 0 if and only if u and v are orthogonal. That's our definition of what it means to be orthogonal. So if this is 0, it drops out, and we have this equality. If this is not 0, we don't have that equality, okay? And so that's it. That's the Pythagorean theorem proof. Now I'm going to back up to that statement up above. So here's where we're entering a brand new world. So I got to slow down a little bit. So I should have, again, highlighted this in some way. Let W be a subspace of Rn. Consider the set of vectors in Rn that are orthogonal to every vector in W. So let me try to picture. Here's a simple picture might be W might be the xy plane of vectors, all the vectors in the xy plane. And so if you consider all the vectors in Rn that are orthogonal to every vector in W, that's going to be like the z-axis. It's not going to be anybody over here, because a vector coming out this way, that's not making a 90-degree angle with all the vectors in W. So in R3, because we don't have too many dimensions to work with, if W is two-dimensional, this thing we're going to call W perp, and I guess I haven't officially said what it is yet, is going to be one-dimensional. If W was one-dimensional, W perp would be two-dimensional. The dimensions we're going to see are going to add up to n. We'll see that eventually. So anyway, consider the set of vectors in Rn that are orthogonal to every vector in W. This is called the orthogonal complement of W. And this is the orthogonal complement of W. This is the notation we use. But everybody reads that as W perp. Okay? And this is something that's going to be a big part of everything we do in chapter 6 from now on, this idea of W perp. Okay? So let's just turn the page to the theorem, which goes along with what we just said there. So this is important, and it's not hard either, not hard at all. Let W be a subspace of Rn. Let S be a set that spans W. Okay, so S is a spanning set of W. Could be a basis, could be more than a basis. All right. So think of S is some subset of W, and if you take all the linear combinations of the elements of S, you get all of W. Right. So it could be a basis, possibly. So part one of the theorem, X is in W perp, this orthogonal complement, if and only if X is orthogonal to every element of S. Number two, W perp itself is a subspace of Rn. So W is a subspace. We talked about this set of all the vectors that are orthogonal to W. Maybe it's a subspace, maybe it isn't. Well, it is a subspace. It's not hard to show that. And W intersect W perp. This is for any subspace at all. They're only going to intersect at the 0 vector. So they're not going to cross over. And you can kind of see here the xy plane intersects the z-axis only at the 0 point. There are a lot of other vectors in R3 that are not elements of W or W perp. That used to be kind of confusing for me. So just notice we could, if I'm drawing arrows, if I come out over here or over here, those are examples of vectors that are not in W, not in W perp. There's a way to get them, though. However, if I come straight down from the z-axis, again, all the vectors along here are going to be in W perp. Okay. So let's prove these points of the theorem. These are real easy items to prove, really. Number one, X is in W perp if and only if X is orthogonal to every element of S. Actually, I'm just going to let you read through that on your own, because it's really not that profound. It's really the if part. If you know X is orthogonal to every element of S, then let W be any element of W. W is a linear combination of elements of S, since S spans W. So any element of W can be expressed in this way. And if you take X dot W, where what was my X? My X was in W perp. Then X dot W will be X dot this stuff, which we can expand. And you end up taking X dot each one of the spanning vectors. But we're saying if X is orthogonal to every element of S, all those dot products have to be 0. So the dot product of X and W has to be 0. That's just not really that amazing. And the second point, that W perp is a subspace, that's really easy to show also. That starts right here. Note that 0 is in W perp, since 0 is orthogonal to all vectors. Let X and Y be in W perp. Let W be any element of W. We want to show that X plus Y dot W is also 0, right? Well, X plus Y dot W is X dot W plus Y dot W. Those are both 0, 0 plus 0 is 0, so x plus y dot w is 0. I mean, it really is that straightforward. So x plus y is in w perp. If you take a scalar multiple of a vector that's in w perp, we can factor the scalar multiple out from the dot product. So c times 0 is 0, so cx is in w perp. And finally, let x be in the intersection. So is that, I hope that symbol isn't, am I throwing out a mysterious symbol that no one's ever seen before? So when we show that, use that upside down U, that means intersection, that means the overlap of these two, right? Let x be an element of both w and w perp. Since x is in w perp, x dot w is 0 for all w in w. Just turn the page. Last page now. But x is in w, so set w equal to x. So that means x dot x is a potential x dot w. But if x dot x has to be 0, then the only way that can happen, the only way the dot product of a vector with itself can be 0 is if the vector is 0. Now, theorem 3 is a little bit more profound, and this is the MIT professor who's got his course online. He gets all excited about this stuff. And it is kind of an exciting result now. So we're going to relate row space, column space, null space to this orthogonal complement space. Okay? Like, whoa, where's all this happening? So these are two big results that'll take a little while to get used to, and yet we are going to work with them quite a bit. So we got to get this down. Row space of A perp is equal to null space of A. Column space of A perp is equal to the null space of A transpose. So let's just draw a couple pictures here first. So A is m by n. So A represents a linear transformation from Rn to Rm, right? That's multiplication by A. Where are all these spaces that we're talking about? Where's the row space of A? Rn or Rm? Our row space of A is we think of as sitting inside the domain space, right? Because those are going to be vectors with n components. There are m rows, but there are m spanning elements that we have, but the number of components in each element is n. Where's null space? Null space is also in the domain. So, in fact, we made this observation a while ago, that both of those can be thought of as subspaces of Rn. And what this theorem is saying is there's a relationship. So I think we can just say they're orthogonal complements of each other, actually, but the statement of the theorem says the orthogonal complement of the row space of A is the null space of A. So it's sort of like if we had a picture of Rn, now I don't, this is going to be different in different situations, but I'm going to copy my previous picture. The row space of A could possibly be the xy plane, I don't know, in one particular example. And then the z-axis could be the null space of A. I mean, this is just one possible scenario. There's no reason why the null space of A couldn't be two-dimensional or even three-dimensional, the whole space. And these subspaces, really any line through the origin could be one of these subspaces. Any plane through the origin could be one of these subspaces. I'm just being lazy and drawing my picture. But it's nice to have some sort of a picture. And of course, in Rn, the situation's more complicated because we have more than 3 dimensions to work with. So that's just trying to frame this a little bit. And the column space of A perp is equal to the null space of A transpose. So we know the column space of A is the range, really, of a linear transformation. So column space of A perp is also going to be in Rm, and that's equal to the null space of A transpose. Now, A transpose defines a linear transformation in the reverse direction. At least that's one way you can think of what's going on. So Rm is actually the domain of the linear transformation defined by A transpose. So again, what we're saying here is the column space of A perp is equal to the null space of A transpose. In terms of Rm, I didn't give myself much room here, but let's just put a little picture. So I'm using R3 again, because that's the only multidimensional space I can draw very easily. We're saying you got this column space, this range of linear transformation sitting inside of Rm. The perp to it is the null space of A transpose. So that, to me, that's like, what? I would have to, that'll take a few days for me to sort through. Let's put a box around this, since that's the second component of the theorem. But just right now, you just want to say this first equality is taking place inside of Rn, the domain space. The second equation is taking place inside of Rm, the range space of a linear transformation. So let's prove it now. Okay. So first, we're just going to prove the first line. The row space of A perp equals the null space of A. With me? Okay. And I'm going to run through a sequence of if and only if statements. So the logic goes both ways. So first, let's say, suppose X is in the null space of A. All right. So I'm going to have to show that X is in the row space of A perp, right? So I'm starting with a vector in this guy, the null space of A. X is in the null space of A. What does that mean? Well, it's if and only if AX equals 0, right? It's a solution to the homogeneous equation. That's if and only if the following statement is true. Now, that's not obvious to me. Let's talk about this a little bit. So AX is going to be a column vector where each element of that column vector can actually be thought of as the inner product of a row of A with the X vector, row 2 of A with X, all the way down to row M of A of X, because A has M rows. And to say those are equal to, that's AX equals 0 means we have the 0 vector on the right-hand side. So each one of those dot products has to be equal to 0. Now, I don't know. This I'd pause a little bit on. Like, we have a lot of ways of thinking of what. Let's just pretend we're in R3. So suppose A is 3 by 3, just so I can draw a picture. And I'm just going to put A, B, C, D, E, F, G, G, H, I for the elements of A. X then has to have 3 entries, X1, X2, X3. This multiplication can be thought of as X1 times the column vector A, D, G, plus X2 times B, E, H. This isn't the only way to think of this, but we're used to doing this, right? When we take A times X, we're taking a linear combination of the columns of A with the components of X's weights. But do you see what I'm going to get now? I'm going to get, across my first row, I'm going to get ax1 plus bx2 plus cx3. Oh, all right, now you see, right? What does that look like? That looks like the dot product of the first row of the matrix A with the, oh, that's just our calculation too. I'm going around in circles, right? I should have just gone to the abstract. But it's still worth pausing a little bit on this, because we're not used to thinking of that as an inner product calculation, right, when we multiply. Again, I could have just went across the first row, down this column, across, down, to get these entries. So that's just a specific example where this is 3 by 3, right? So this is not profound. You guys should be looking at it saying, oh, yeah, all right? But what that's saying is x is orthogonal now. We can interpret that to each row of A. If x is orthogonal to every row of A, x has to be in the row space of A perp, the orthogonal complement of the row space of A, because the rows of A span the row space. So we're saying that x is orthogonal to every element of a spanning set of the row space. So it has to be in, it's got to be in the perpendicular complement space here. Okay. Boom, that's done. That's the first equation. Second equation is to show the column space of A perp is equal to the null space of A transpose. We kind of piggyback on what we already said. The column space of A is the row space of A transpose. So the column space of A perp is the row space of A transpose perp. So we're just going to make use of this first equation, but we're going to be talking about A transpose instead of A. So that's equal to the null space of A transpose. Oh, we're done. Boom. All right. Now, this is a horrible picture, and I really should delete it. So you might want to even just cross it out. I reached the limits of my artistic skills. I think this picture might be better for you, or this picture in this picture. I was trying to show higher dimension somehow. This is not a picture in R3, because I'm trying to say, well, what if the row space is two-dimensional and the null space of A is two-dimensional? That could only happen in R4 or higher. And the problem of trying to show them perpendicular to each other, they're only going to intersect at 0. In R4, you can have two planes that intersect at one point. You can't draw that in R3. So that's why this is a horrible picture, because it's not a picture in R3. I'm trying to draw a tesseract or something here, and I'm not succeeding, or whatever. This is just, I'm just trying to say row space of A is perpendicular to the null space of A, is what I'm trying to say. That's one way of thinking what this theorem is, but they're not going to intersect along a line. They're only going to intersect at 0. So that's deceptive, the way I drew that picture. And the column space of A in Rm is perpendicular to the null space of A transpose. Again, they're not going to intersect in a line. They can only intersect in the 0 vector. So this is an impossible picture in 3D, and it's probably should be removed from the handout. And that's the end of 6.1. And we got, oh, shoot. I was hoping we'd have a couple more minutes. So I'm going to give you the 6.2 before we quit today. And yes, I realize that was pretty much a problem-free handout. We didn't do any exercises. But just give me a couple more minutes to introduce 6.2. And we'll be calculating away pretty soon so we can get a more hands-on feel for what's going on here. So 2 minutes of 6.2. Show you where we're headed. So we're going to do a lot of talk about what are called a set of vectors that's an orthogonal set. Could be a spanning set sometimes, could be a basis, could be different things. What does it mean to be an orthogonal set? It just means if you take the inner product of any two different vectors in that set, you're going to get 0. So the vectors are all perpendicular to each other, or orthogonal to each other. Every U1 is orthogonal to all the other ones. U2 is orthogonal to all the other ones up and down the line, right? With two vectors, you know, we have a sense there's only one way they can be orthogonal to each other. With three vectors in R3, your famous I, J, K vectors, I, J, and K form an orthogonal set. There's no connection to the I and J here, right? This is just a subscript. It's got no vector meaning, the I and J use here. So theorem 4, let's just state this and then we'll call it quits. Any orthogonal set of non-zero vectors, so orthogonal set could have a 0 vector in it, and that's not very interesting. So if they're all non-zero vectors and they're orthogonal, they have to be linearly independent. And so their span, which is a subspace, that's always going to be a basis for the span of those vectors, because that's a linearly independent set that spans the span of S. And I'll stop right there. Better stop. So it's getting interesting now. See you on Wednesday.